What you are seeing is footage recorded on January 22, 2026, when the interstellar object 3I Atlas passed through an alignment so rare it was almost unimaginable. For the first time, humanity observed it from nearly the direction of the Sun, in a full-phase view, with no shadowed regions and no blind angles. But the surprise did not stop there. Instead of stretching away from the Sun like every known comet, its tail pointed in the opposite direction, almost straight toward Earth. This paradox forced Avi Loeb and many other scientists to pause and seriously question the true nature of this object. Loeb has also suggested that the combination of 3 jets and a central outflow in 3I Atlas shows notable similarities to spacecraft design principles, meaning the possibility of an extraterrestrial technological origin cannot be completely ruled out. Right now, stay with us until the end of the video to witness this rare moment for yourself and understand why 3I Atlas has become one of the most challenging questions in modern astronomy. "3I Atlas matters because it is not just another object passing through our sky, but a rare visitor that comes from beyond the solar system. In simple terms, interstellar means it was not born around our Sun. It formed around another star in a different system under conditions we can only infer from distance and light. Now it is briefly crossing our neighborhood, a one-time encounter before it disappears back into deep space. What makes this visit especially important is how few similar objects scientists have ever been able to study. So far, only 3 interstellar objects have been confirmed, which means each one serves as a fragile and limited data point rather than part of a large population. Unlike planets or asteroids, where thousands of examples help scientists build reliable models, interstellar visitors arrive without warning and leave before close study is possible. This puts science in a reactive position, where researchers must work with whatever data they can collect in real time. There is no opportunity to plan missions years in advance or send spacecraft to intercept the object up close. As a result, almost everything we learn comes from telescopes on Earth or in orbit, observing from millions of kilometers away. That limitation is exactly why the observation on January 22, 2026 became such a critical moment. On that day, 3I Atlas passed through an alignment so precise that Earth viewed it almost directly from the direction of the Sun. The angle difference was only about 0.69 degrees, creating a full-phase view similar to seeing a full moon. In this geometry, the object reflected sunlight evenly, without large shadowed regions hiding its surface. For astronomers, it was like turning on a light in a room that had always been dim. According to Avi Loeb, moments like this are extremely rare, especially for objects that do not belong to our solar system. The timing was not planned, not controlled, and impossible to repeat, which made every second of observation unusually valuable. Even so, this clearer view did not solve the deeper problem facing scientists. They could track how 3I Atlas moved, how fast it traveled, and how its brightness changed over time, but its internal structure, composition, and physical strength remained hidden. This gap between what is visible and what remains unknown defines the tension surrounding 3I Atlas. Researchers are watching an object behave clearly in space while still lacking firm answers about what it is made of or how it holds together. That uncertainty forces scientists to rely on indirect clues rather than direct measurements. Small changes in brightness, subtle shifts in shape, and unusual reflection patterns suddenly become meaningful signals. Because interstellar objects are so rare, even minor details carry far more weight than they normally would. A feature that might be ignored on a familiar comet can suggest a very different formation history in this case. At the same time, scientists must stay cautious, because unfamiliar behavior does not automatically mean something artificial or extraordinary. This balance between curiosity and restraint explains why 3i Atlas is being monitored almost day by day. It offers a chance to test ideas about how planetary systems form beyond our own. It also reminds researchers how limited current knowledge still is when facing visitors from other stars. As this careful observation continued, attention naturally shifted away from where 3i Atlas came from and toward what it was doing in plain sight. That shift would soon lead scientists to focus on one specific feature that stood out far more than expected. The most striking feature of 3i Atlas is not its speed or its origin, but the direction its material takes as it moves through space. In normal comets, dust and gas are pushed away from the sun by solar radiation and the solar wind. This is why comet tails almost always stretch outward, forming a familiar shape that points away from the sun. For decades, this behavior has been so consistent that it became a basic rule in astronomy. 3i Atlas breaks that rule in a way that cannot be easily ignored. Instead of forming a tail that trails behind it, the object repeatedly shows an anti-tail, a plume of dust and gas that points back toward the sun. This is not a visual trick caused by camera angle or viewing position. Multiple observations confirm that the material is physically oriented in that direction. When astronomers first noticed this behavior, it immediately raised concerns about how 3i Atlas interacts with solar forces. In some comets, an anti-tail can appear briefly because of perspective effects when Earth crosses the comet's orbital plane. In those cases, geometry creates an illusion, and the tail only seems to point toward the sun. What makes 3i Atlas different is that its anti-tail appears consistently and remains stable across different viewing angles. That persistence suggests a real physical process rather than an optical coincidence. The observation on January 22, 2026 made this anomaly impossible to dismiss. On that day, Earth observed 3i Atlas from almost the same direction as the Sun, with a separation of only about 0.69 degrees. This alignment created a full-phase view, similar to how a full moon reflects sunlight directly toward Earth. Under this lighting, shadows fade and surface features become easier to interpret. At the same time, the anti-tail was oriented almost straight toward Earth. For the first time, scientists could observe the structure face-on instead of from the side. This removed much of the uncertainty that usually surrounds tail observations. According to Avi Loeb, this configuration offered a rare chance to study how the material was organized and how it behaved under solar pressure. What stood out was not only the direction of the anti-tail, but its coherence. The plume did not disperse quickly or collapse into chaos under radiation forces. Instead, it maintained a defined shape over time. If the anti-tail were made of ordinary dust released randomly from the surface, solar radiation should have distorted it rapidly. The fact that this did not happen adds another layer to the mystery. Researchers began to consider whether the material might be heavier than typical comet dust or released in a more structured way. Neither explanation fits comfortably within standard comet models. This is especially puzzling given how far 3i Atlas was from the Sun when this behavior was observed. At such distances, solar heating is weaker and strong directional outflows are less common. Yet the anti-tail persisted, resisting forces that normally dominate small bodies in space. The face-on view also allowed scientists to study how light scattered across the surrounding dust. The reflection pattern suggested structure rather than randomness. Instead of a smooth fading cloud, the region around the nucleus showed boundaries and gradients. These details did not provide answers on their own, but they narrowed the range of plausible explanations. They also made it harder to dismiss the anti-tail as a minor curiosity. As more data accumulated, the anti-tail began to look less like an odd feature and more like a defining characteristic of 3i Atlas. Understanding this plume became essential to understanding the object itself. The anti-tail was not just pointing in the wrong direction, It was behaving in a way that challenged long-held assumptions about how small bodies lose material in space. This realization gradually shifted attention toward what might be happening on the surface of the object. As researchers focused more closely on the region near the nucleus, new details started to emerge from the glare. Those details would soon introduce geometry into the discussion and push the investigation into far more unsettling territory. One of the earliest signs that 3I Atlas was unusual appeared long before it came anywhere near the Sun. In most cases, comets remain quiet while they travel through the cold outer regions of space. At large distances, sunlight is too weak to heat the surface enough to drive strong outgassing. This is why most comets only become active when they move closer to the inner solar system. Water ice begins to sublimate, gas escapes, and dust is dragged outward to form visible tails. This pattern is so consistent that it has become the basic framework for understanding comet behavior. 3I Atlas did not follow this familiar path. Astronomers observed signs of activity while the object was still very far from the Sun. At that distance, water ice should have remained frozen and stable. Yet material was clearly being released into space. This early activity immediately suggested that a different process was at work. Scientists began looking beyond water ice for an explanation. Some compounds, such as carbon monoxide and carbon dioxide, can sublimate at much lower temperatures. If these substances exist beneath the surface, they can drive activity long before a comet warms up. This idea offered a reasonable starting point, but it did not resolve everything. Many comets contain small amounts of these volatile materials. What makes 3I Atlas different is the apparent consistency of its activity. Instead of brief or irregular bursts, the outflow appeared steady over time. This implies that the source of the material may be distributed in an organized way. Random pockets of ice would be more likely to produce uneven behavior. The sustained nature of the activity hints at a structure that can regulate how material escapes. This detail matters because it points back to how the object formed. If 3I Atlas developed in a much colder environment, volatile compounds could be preserved in greater quantities. Such conditions are more likely in distant stellar systems or the outer regions of protoplanetary disks. That possibility strengthens the idea that this object carries chemical signatures from another star system. Early activity also complicates how scientists evaluate future behavior. An object that becomes active far from the Sun can be detected earlier. However, long-term outgassing can slowly alter its motion and rotation. Small forces acting over long periods can create large changes. This makes predictions more uncertain, especially for an object already behaving unusually. The steady release of material also raises questions about physical strength. A loosely bound rubble pile would be more likely to fragment under prolonged stress. So far, 3I Atlas has shown no clear signs of breaking apart. This suggests a more coherent internal structure. It may have a solid outer layer that allows gas to escape without immediate collapse. Such a configuration is not impossible, but it is not common either. Each new observation adds pressure to standard models, rather than fitting neatly inside them. The early activity also affects how brightness changes are interpreted. When an object brightens far from the Sun, several factors may be involved. Gas emission, dust production, and surface changes can all contribute. In the case of 3I Atlas, these effects may be overlapping in unfamiliar ways. This makes simple comparisons with known comets unreliable. Instead of matching a single category, the object displays mixed characteristics. That complexity is typical of interstellar visitors. They are shaped by histories that differ from anything in our solar system. By the time they reach us, they may already reflect processes we rarely observe. As scientists tracked this early activity, attention gradually shifted toward the region near the nucleus. There, additional features began to appear that could not be explained by chemistry alone. What truly pushed the discussion around 3I Atlas into uncomfortable territory was not its speed or brightness, but the discovery of structure where randomness was expected. When astronomers analyzed high-resolution images of the object, they did not simply look at the raw glow surrounding it. They applied processing methods designed to remove the smooth, symmetrical halo of dust and gas that normally hides finer details. Once that background was stripped away, something unusual appeared. Instead of a chaotic spray of material, researchers saw 3 distinct mini-jets emerging from the nucleus of 3I Atlas. These jets were not clustered together or scattered unevenly across the surface. They were spaced at nearly equal angles of about 120 degrees from one another. In astronomy, symmetry matters because natural systems tend to be messy. On most comets, jets form where sunlight happens to hit pockets of ice, and those pockets are distributed irregularly. As the comet rotates, jets flicker on and off in unpredictable ways. A stable, evenly spaced pattern is difficult to maintain without some form of underlying order. Avi Loeb emphasized that this was not a single snapshot or a momentary illusion. The 3-jet pattern appeared repeatedly after the data was processed, suggesting it was tied to the object itself rather than noise or chance alignment. This is where the tension begins. If the surface of 3I Atlas were covered in random patches of volatile material, there would be no obvious reason for them to activate in such a balanced geometric layout. Geometry implies constraints. Constraints imply structure. At the same time, Loeb was careful to avoid jumping to conclusions. Seeing order does not automatically mean design. Nature can sometimes produce patterns that look intentional, especially when rotation, internal stresses, or layered materials are involved. Other researchers pointed out that fractured crusts or internal pressure chambers could, in theory, channel gas through preferred pathways. However, those explanations often struggle to explain why the spacing remains so clean and consistent. Supporting observations from other telescopes added to the complexity. Some images showed the jets changing strength over time, blinking on and off rather than flowing steadily. This created what some analysts described as a spider-like appearance, with multiple arms extending from a central point. That behavior suggests active regions beneath the surface that are distinct from one another. Instead of one large vent, the object appears to have several smaller ones working in coordination. For viewers, the key point is not that this proves anything extraordinary. The key point is that it breaks expectations. Scientists are comfortable when objects behave in familiar ways, even if those ways are extreme. They become uneasy when patterns appear that do not fit existing categories. With 3I Atlas, the presence of 3 evenly spaced jets shifts the conversation from simple chemistry to internal organization. It forces researchers to ask whether the object's interior is layered, segmented, or shaped by forces we do not yet understand. This does not mean the object is artificial. It means the usual models for comet behavior are being stretched thin. In science, moments like this are important because they reveal the limits of current explanations. They do not close the case, they open it wider, and as attention moves from visible structure to the forces driving it, the next focus naturally becomes the object's motion and stability under stress. One of the most difficult aspects of 3I Atlas to explain is how strongly it accelerates without tearing itself apart. In space, most objects move according to gravity alone, following paths that can be predicted with high accuracy. Comets are an exception, because when gas escapes from their surface, it can act like a weak engine and slightly change their motion. This effect is called non-gravitational acceleration, and it is well known to astronomers. Normally, however, this push is modest and uneven, and it often comes with visible consequences. When a comet is pushed too hard, its nucleus cracks, fragments, or becomes wildly unstable. With 3I Atlas, scientists are seeing something different. Measurements show clear signs of non-gravitational acceleration that go beyond what is typical for objects of this size. At the same time, the nucleus remains surprisingly intact. There is no obvious breakup, no spreading debris cloud, and no sudden loss of shape. This creates a contradiction that researchers cannot ignore. If the forces acting on the object are strong, why does it still behave like a solid body? Data discussed by Avi Loeb points to an organized pattern in how these forces are applied. Instead of random bursts pushing in all directions, the acceleration appears structured and directional. This idea is often described as organized asymmetry, meaning the forces are uneven but not chaotic. Such behavior suggests that the internal layout of 3I Atlas plays a major role in how it responds to stress. Rotation adds another layer to this puzzle. Brightness variations indicate that the object completes one full rotation in about 7.1 hours. As it spins, the jets do not simply flicker randomly. They wobble in a repeatable rhythm, similar to a lighthouse beam sweeping through space. This means the acceleration is tied to rotation rather than acting independently of it. In simple terms, the object seems to push itself in a controlled pattern while spinning. For a fragile pile of ice and dust, this level of coordination would be unexpected. This leads scientists to consider alternative natural structures. One possibility is that 3I Atlas has a largely solid, monolithic core rather than a loose rubble pile. A solid interior could survive stronger forces without collapsing. Another idea is that it has a tough outer shell that traps volatile gases beneath it. As pressure builds, gas escapes through specific vents instead of bursting the object apart. This would allow powerful jets without immediate destruction. Even these explanations come with challenges. A structure strong enough to remain stable should also limit how violently material escapes. Yet the observed activity suggests significant energy release. That balance between strength and volatility is not easy to model. What makes this more unsettling is how long the object maintains this state. It does not show the rapid decline or fragmentation seen in many active comets. Instead, it continues to behave consistently over time. For scientists, consistency is often more troubling than chaos. It implies an underlying mechanism that is doing exactly what it is supposed to do. Still, caution is essential. Unusual does not mean unnatural. Nature has a long history of surprising researchers with structures that seem impossible at first glance. The correct explanation may involve chemistry and physics that are simply rare in our solar system. Because 3I Atlas formed around another star, its internal makeup could follow rules we have not encountered before. This is why the object's stability is not treated as evidence, but as a pressure test for existing theories. As long as it holds together under increasing stress, it continues to raise the stakes. And as it moves deeper into the gravitational influence of a giant planet, the next phase will determine whether this balance can survive a far greater challenge. March 16th, 2026 is not just another date on an orbital chart, because it marks the moment when 3I Atlas enters Jupiter's gravitational influence. For scientists, this approach functions like a natural stress test. No laboratory on Earth can reproduce. Jupiter is massive enough to reshape trajectories, amplify forces, and expose weaknesses in objects passing nearby. If 3I Atlas is an ordinary natural body, its path should bend smoothly, following well-understood gravitational rules. Any activity caused by sunlight-driven outgassing should remain consistent with what telescopes have measured. But if something unusual is hidden beneath the surface, Jupiter is where it may reveal itself. One question raised by Avi Loeb is whether 3I Atlas could release smaller fragments during this encounter. For a fast-moving interstellar object, dropping material that remains bound to Jupiter would be extremely difficult. The relative speed is high, and the energy required to slow debris enough for capture is enormous. That is why even a single retained fragment would challenge standard comet models. Several spacecraft will be watching this region closely. Juno is already orbiting Jupiter and can monitor changes in the surrounding environment. Jupiter Icy Moons Explorer and Europa Clipper will add further coverage and independent measurements. Together with ground-based telescopes, they create a rare observation network. There are only a few realistic outcomes. Nothing unusual happens, and gravity behaves as expected. A debris field appears, suggesting structural complexity without implying technology. This moment matters because it moves the discussion from speculation to testing. Until now, arguments have relied on distant observations and indirect clues. Near Jupiter, physics takes control, and theories must survive real conditions. Whatever happens, the data will narrow explanations over time. After this encounter, 3I Atlas will be judged by how it responds when the solar system pushes back strongly today. The technology hypothesis appears not because scientists are chasing science fiction, but because certain patterns in 3I Atlas remain difficult to explain using standard comet models. This idea begins with structure, not belief, especially the repeated observation of 3 mini-jets arranged with near-perfect symmetry around the object. In most known comets, gas and dust escape from uneven ice pockets that activate unpredictably as sunlight heats the surface. That process usually creates messy, shifting outflows that change shape over time. 3I Atlas behaves differently, showing ordered activity that stays consistent across multiple observations. The stability of its anti-tail adds another layer to the puzzle. Instead of dispersing under solar radiation pressure, this feature remains narrow and organized. Together, the jets and anti-tail form a balanced configuration that appears controlled rather than accidental. Some aerospace engineers have pointed out that similar layouts are used in spacecraft to manage rotation and distribute force evenly. This comparison does not imply intelligence, but it explains why the geometry draws attention. According to Avi Loeb, resemblance alone is never proof. He stresses that no direct evidence of technology has been detected so far. There are no radio signals, no artificial materials, and no mechanical components visible in any data. For this reason, the technology hypothesis remains an open question, not a conclusion. It exists because current natural explanations are under strain, not because science has found something artificial. One natural model suggests a hard outer shell containing internal pockets of volatile gases. These gases could release energy in a structured way without destroying the object. Another explanation points to an unusual composition shaped by formation around a colder, distant star. Such an origin could produce behaviors unfamiliar to objects formed in our solar system. Both ideas remain possible, but neither fully explains the symmetry without adding new assumptions. This uncertainty is where responsible science slows down instead of speeding up. Loeb has repeatedly warned that turning anomalies into headlines damages public understanding. He has also criticized the spread of AI-generated videos that present speculation as fact. Misinformation, he argues, is dangerous because it replaces evidence with emotion. The correct response is patience and careful analysis over time. In this role, the technology hypothesis acts as a boundary marker for current knowledge. It shows where existing models struggle and where new thinking may be required. For now, 3I Atlas remains unresolved rather than explained. Its nature will be shaped by future observations, not online speculation. And until stronger evidence appears, restraint remains the most scientific position available. 3I Atlas is not important because it proves anything extraordinary, but because it exposes how much we still do not know about visitors from beyond our solar system. Its rare alignment, its unusual anti-tail, its early activity, and its striking symmetry all challenge familiar models without breaking them outright. For now, science stands between curiosity and caution. As new data arrives, especially from its encounter with Jupiter, this interstellar guest may not give us answers, but it will force us to ask better questions.